Hi, I'm Jesse Burns. I'm from ISEC Partners, and I've been doing Android application security for a little while now, and I'm happy to be here and able to talk to you today. Just going to go over a little bit of the basics of Android security. Maybe it's a little better now. Okay. I'm Jesse Burns. I'm going to talk about Android security and Android permissions. Seeing a lot of confusion about the Android security model, and a lot of really good interest from people about how to make mobile applications more secure. Android's pretty fun because it's an open platform, and it highlights a lot of the sort of things we might want to try to do with a new operating system, and an approach to sort of making operating systems more secure. So one of the reasons why Android security's become really exciting in 2010 is that we've got a huge number of Android devices on the way. So we've already got a ton of phones out there, but we're looking at over 2 dozen upcoming smartphones in the next year, and over 3 dozen tablets, which I think tablets is kind of funny because, of course, Android wasn't really marketed as a tablet operating system, and it'll be neat to see how that works. I mean, there's already a bunch of tablets out there. That's a new kind of place for us to go. And then Google TV also was just released. Saw it at Best Buy before I came to Switzerland, and that's a TV application. There's actually TVs now with this embedded right into them. So it's kind of a fun thing. The one that I saw, I just went up to it in Best Buy and poked around a little bit and saw that it didn't have the ability to turn on AVPs. So maybe it's not quite as much fun yet. But they say in the advertisement that by the middle of next year or something, it's supposed to have support for market applications. It seems to be able to, maybe not savvy. So first, coming after Harold, it's hard to kind of beat his level of stuff. This is a slide I had to add because I'm going right after him. So of course, when you look at a phone, you have all these network protocols, things way below the level of Android that we can't change, things like CDMA and GSM. I'm sure we kind of deal with them, but we mostly are abstracted away from them. We then have this whole level of radio baseband software. So the low-level bootloaders, the things that control memory access on the device. And this software is, again, completely out of the scope of Android. It's not part of the open source code. It's not something that's necessarily even different between devices that run Android and devices that run other operating systems. So, you might have the same baseband on some Windows mobile phone and an Android device, because that's it's kind of like the BIOS in a computer or something. It's underneath, and it's really interesting, but it's not at all what I am talking about. I'm just talking about this part at the top here, the Android system, the runtime and the apps. And there's definitely security issues that come up in all these lower layers, and it's really important that we understand them and we mitigate them. But one of the things that's great about having an open Android system is we're kind of used to the idea of having an insecure network that we can't trust computing, right? We have computers that run on the internet, and we all know that that thing is totally untrustworthy, and anyone can hijack your TCP connections, and Provisional Sheriff can decide to pretend to be YouTube, and that's just the way it goes. So we're kind of used to the idea of building applications on top of things we don't trust. But if you can execute arbitrary code, well, that's too much mistrust for us. So let's just talk a bit about how Android represents security. So a lot of people get really bewildered by this because Android, you hear Java, you see a Java programming environment, and you think, oh, I know what Java security is. That's that thing where you can put applets on your websites and they can't do anything bad, right? Well, one of the sample applications on Android is the terminal. So that's a shell, right? You type in there and run programs. That should let you realize that on Android, you can run code, you can write stuff to files, you can use that. It's Linux. So when you think of Linux, you think, oh, I know what that is. It's a multi-user system, and it's a cell phone, so you're just going to be one user, right? Well, not really. On Android, the applications are isolated. And so it's not the user's identity. It's not you're root, you own the phone. It's, oh, this is a terminal application. This is a Tetris video game. This is a little abduction game. right? So here I ran a little abduction game that I installed, and this is the process it runs as. It's called au.com.fill. That's the package name. On Android, the package name of the program is sort of like its true name. Really important kind of concept. But when you look at it, it's not running as Jessie, right? It's running as app45. And the next time I run it, it's also going to run as app45. And that's kind of key because when it was installed, it was given its own unique user ID and its own Linux group ID. And now it always runs as that. So it can't read my email because it's not my UID, or it doesn't have the UID of my email. So it can't access the email database or the email school. So we're using Linux isolation, but we're not using it on a per user basis, we're using it on a per application basis. So, and another side effect of this approach is that native code versus Java code doesn't matter, right? If I have Java code, it can call native stuff. If I have native code, it can call Java stuff. We're not using any kind of security. In fact, we're not even really using Java, we're using Java. It's just the Java language. All right. It's also, oh yes, and one of the other big misconceptions that you see is the Dalvik virtual machine. That must be some kind of security barrier. There was just a paper written. These guys did some great work, and I don't mean to say that their work isn't great. In fact, they pointed out some really serious problems by saying, or showing that some applications were grabbing sensitive information and sending it up. But the way they did it was they instrumented the Java virtual machine, right? That doesn't work. I mean, it might work, and in fact, they found some great results. But an attacker can bypass that, because your code doesn't run in the Java virtual machine. Your code is just a native process running on the machine. You can exec something else if you want to be in a different UI or a different PID. You can execute native code to your heart's content. So if you think that by hooking some Java library, you're going to be able to see what a process is doing, you're only right if you're lucky. If they decide to do it some other way, you're out of luck. So Dalvik isn't a security barrier, and it's such a complicated thing that you wouldn't really want it to be a security barrier. Why, we've already got the Linux kernel, it's enough risk. We have to accept it even, kind of any way we go. So why add Dalvik as another layer of something that we have to get all locked down? This is the Android approach. It's also not the iPhone security model. The platform actually restricts applications on Android in a way that's appropriate for what they do. So when you install an app, it says, hey, this app is going to have access to your contacts. It's going to have access to the internet. And that way, if you download a flashlight application, and it actually is operating as a SOX proxy, it's going to fail, because a flashlight doesn't need internet permission. Whereas on the iPhone, you sort of have one vendor that decides whether or not something should be allowed on, and if they make a good decision, that can protect you. But there isn't that same level of permission stopping the applications from actually doing and that lets the platform's applications be more powerful than they would have to be on other systems. And that lets them kind of do more dangerous things, which is great for open development and customization. And it's also not so good if users don't know how to read, or don't care to read, or get confused by permissions that are too complicated. And that's one of the things that's really critical for the system, is making sure that permissions are things that people can really understand. One of the other things that's interesting with Android is that it often supports OTA updates. And I only say usually or often because actually OTA update mechanism isn't part of Android, right? That's part of the Google Experience devices. And there are other platforms like Motorola Blur, which is an Android distribution, which isn't a Google distribution. It has its own update system. It's a separate over-the-air update system. And there are other platforms like the original HTC Hero that shipped. And those platforms don't have over-the-air updates. And so if you want to update those devices, you have to actually go to a website, download something, put it on an SD card, which means you get it on a PC. And that's an important problem for those companies. It's really important when you have something that's based on the Linux kernel that you're able to update it all the time, because we know that over time vulnerabilities appear in that kernel, and you need to be able to patch them. So over the air is. Just want to demonstrate these rights that I've been talking about, these permissions in shells real quick, because I think that's a good way to understand them. when you fire up ADB, this is a program that runs on your computer and lets you get a shell on the device, on an Android device, and see what's going on. You run as this special user called the shell user. I'll talk a little bit more about that later. But you can see when you do an ID that it's got a couple of Linux groups that it's in, including the shell group, because that's just a special account. It's a number under 10,000 special. But it also has graphics and input and log and inet and mount. So those are groups that are associated with Android permissions. Not every Android permission has a Linux group associated with it, but a few do. So like, for example, the inet permission is associated with group 3003. And the reason for that is that you have Linux capabilities that stop people from making IF inet sockets if they aren't in the inet group. And because that's being enforced in the kernel, you need to express that that Android permission is associated with the GID. But maybe a permission like read contacts, which doesn't mean anything at the Linux layer, that permission doesn't require the Linux GID. So some permissions give them, some don't. This next shell down is one that's just the standard terminal app. It comes as a sample application on in the Android SDK. And when you run ID on that, you just see it has the UID app26, because it's the 26th app installed or whatever, and GID of 26. And then the only permission it has that's associated with this group is inet. And then down here I have another kind of crappy old terminal that has no permissions, and so it has no permissions. All right, so permissions like read contacts are granted to applications when they're installed. And they have a couple of interesting properties, like they can be members of groups. So you can say, oh, there's permissions that give away information about you. There's permissions that cost you money. There's permissions that are for accessing accounts. You know, these are kind of groups of permissions to give users like the general idea of the kind of permission that it is, and then there's a little description that needs to be internationalized. They also have a protection level, and the protection level is really important because it controls whether or not developers, third-party developers, can make applications with that permission. So if you have some permission that you think that it's too sensitive to allow users to have you restricted with this. And that can cause all kinds of trouble. But anyway, one key thing about these permissions is they need to be meaningful to real people. Like, it can't be meaningful just to developers. They have to be meaningful enough to developers that the developers can enforce them, but they also have to be meaningful enough to a human who's using the phone that they'll understand what that means. So read contacts, that's a good example, I think, of a permission, because people can understand, hey, a video game doesn't need to read my contacts. But execute native code might mean something to everyone in this room, right? Oh, this program is going to be able to use arbitrary code instead of just Delta constructions or Java bytecode. But it means nothing to most users. And so they'll have no idea why a fractal rendering program that needs to access some vector instruction that wasn't exposed through Java needs that execute native code permission. And they'll just be befuddled by it. And if you befuddle them too much, they'll stop reading the permissions catalogs and they'll lose all meaning. So I really don't like this concept that's been floated by several people of having an execute native code permission or an execute code permission. If you think about it, anyone who wants to can always, even if you take away native code, anyone who wants to can always write an application that embeds a Lua interpreter. And they can download a Lua interpreter off the internet and have it perform kind of arbitrary operations on data anyway. So applications can always update themselves and can always go off onto the internet, download instructions, and then attempt to exploit a vulnerability in the platform. Trying to stop that, like Apple has tried to do with iPhone just by policy, it's probably not productive from an actual security mechanism perspective. It's probably only productive by the way Apple has done it, which is when you accidentally sneak a flash interpreter onto their store, they pull it off a few hours as a result. All right. So, end result, Delphic is not a security boundary, native code is especially not. So, one of the things about this permission model is that there's this normal protection level, and there's this dangerous protection level, and then there's this signature and signature assistant protection level. And these last two are for things that are really dangerous, like the ability to install new programs. If you want to replace the installer for apps, you do that on Android by installing a third-party program. You just need a permission that is synced to the system. And what they mean by system is applications that kind of come bundled with the device. So if I'm an enterprise, I might make my own device, or if I'm a carrier or a phone manufacturer, I make my own distribution of Android. Any of you can make your own distribution of Android. You're going to have this part on the file system called system app. You're going to have a pile of APKs in there, which are just bundled applications that get installed. And if you look in here, you're going to see all kinds of junk, right? This is, I think, off of a Nexus one. And you can see some of this stuff is from Google, like the YouTube APK. Some of it's from Amazon, like the Amazon MP3 one. Some of it, there's stuff from Facebook and Twitter, different kind of companies in there. And one of the things that's really dangerous about things that go in here is that normally when you install an application, you approve it. You say like, oh, I trust Facebook to have access to my contacts, or I trust whatever site to have access to YouTube. With applications that are installed in the system, that approval is already done for you. That was decided by your carrier. Like, oh yeah, everyone that gets our phone is going to have YouTube, and they don't need to go through some approval process to say that's allowed to be on the internet. Because the first thing that would happen with your phone maybe is you would get through 100 of those. No one would read them, and it would just be a bad idea. Anyway, one of the more questionable things about this is that uninstalling these packages is also not allowed. And that's a little bit more problematic. There's this read-only partition that the system is mounted on, and that's where these files all live. So good luck getting rid of this. So what we kind of have now is someone else is making decisions about what applications go onto your device and what permissions they have. And on top of that, because they're in this special system place, they can use more dangerous protections than third-party apps, right? If you wanted to install My Lookout, say, which is this antivirus product, and that one have a feature where it remotely wipes your phone, which would be great. If I lost my phone, I'd like to be able to wipe it. If it was installed off their website, it's not going to have that ability. You can't just destroy everything on my phone. That's not the kind of thing people want third-party apps to be able to surprise them with, right? But if they make a deal with one of the manufacturers, they can drop it into the system folder, and then it can get that kind of right. And those guys can go through some process of vetting them that's more thorough. So that's sort of the design there. Figuring out exactly what those guys do is something that I'll go through in a little bit. It's really important to obviously look at those. Before I do that, I want to just talk a little bit about the user mode toys. These are the building blocks that you build Android apps with. So, I thought I dropped one of those slides. Anyway, activities are one of the main building blocks on Android. They're like screens, like the dialer, and they can be secure. So you can say the only people that can bring up this screen are people that have a particular permission, right? And that means, if someone goes through the launcher, well, the launcher has some permissions, so it's going to be a problem. But if I have like maybe the restart screen, which just brings up the screen that says, hey, your system's restarting, sorry. That can't be done just doing it. Services, also securable. They expose themselves. They run in the background, so you can have an IM service or something that doesn't need to have user attention to stick around. Broadcast receivers are for asynchronous notifications, so you have a program that doesn't take up any memory, doesn't run, doesn't use your battery until some exceptional condition happens or someone triggers it. And then content providers are a relational data store, and all of these can be secured really nicely with Android permissions. So you don't have to fiddle around with file system permissions, which aren't as expressive, right? And aren't as understandable by users. So I can have this brick permission, and I can have a broadcast receiver that receives brick, and it never gets loaded into memory until the day that the authorized party says, "Time to break the phone." And then it fires up and starts. That's the slide. Anyway, the enforcement of these is done through Activity Manager. Activity Manager is the thing that's responsible for actually enforcing a lot of this and for starting up the applications and for controlling their life cycle. It's kind of a key security component of the platform. And it sends and receives broadcast intent. So if you say I'd like to send a broadcast, it's the thing that decides, yeah, that's allowed, or hey, you have to have this right. It starts services, it does intent dispatching, and it kind of coordinates the accessing of content providers. It can also kill and manage processes for you. So there's a new right that just appeared in Froyo called Kill Background Process. And if you have that right, you can call into the activity manager and say, hey, could you please murder this process for me? Because one of the things people wanted was the ability to kill processes. That was a common thing on that kind of stories. Package Manager is the system software manager. And it's the thing that makes a lot of security decisions about the platform. It knows about what rights what apps have and what signatures they have. And when you install an application, it's the thing that makes the decision, hey, this application that is being installed is actually a new version of your web browser. And so it's okay to have your cookies, right? Or this is a new version of the email client we have, so it's okay for it to update that old version and still have access to your mails for you. That's a pretty key function. It gets called all the time. And modification of it, because it's all open source, of course, will allow you to customize control of permissions on the platform. So I hope that an Android open distribution is going to emerge at some point. And when such a distribution emerges, a custom package manager might be one of the things that it would support, because there's a lot of stuff you could do here that would allow you to experiment with more kind of interesting security models. Other ways of kind of authorizing things. Like maybe you could have GNOME-approved packages that you can install onto your Android device. And that way, someone who doesn't want to read through all those permissions, because some people get confused about them, they could just say, oh, I just want to see ones that have been approved by the vendor I trust. All right, permission enforcement. So Android permissions are enforced differently for each of those IPC mechanisms I mentioned. And their enforcement can be kind of complicated. One of the things that people tend to make a lot of mistakes with on Android is they will think only about one side. So you write a server and you think, I need to verify my clients. Or you write a client and you think, I need to make sure I'm talking to the right server. But you don't do both at the same time. And of course, just like on every other client-server system, you always have to do both or it's not secure. So one of the system services on the machine is this account manager. And the account manager exposes an abstraction to allow you to store credentials on the device so that I can install a bunch of applications and they can use the same credentials without the user having to constantly retype them. So that's kind of a sensitive thing. I have this Gmail account associated with my device. I installed Google Finance. And even though it has a special permission that says that it's allowed to access this, and it warned me before I installed it, even when I go to run this program, it pops up this dialog saying access request. And this is very unusual for Android. This wasn't in the first version of Android that shipped. The general idea with Android is that when you install an application, that's when you're thinking about the reputation of the developer. That's when you're actually going to spend the time it takes to read something, and that's when they ask you to make a thoughtful security decision, right? They don't ask you every time you go to use an app whether or not you intend to allow this application to have access to your personal information, because that's just you're in the wrong mindset of making security decisions. Anyway, so this is just a one-time thing, and so it happened shortly after I installed it. The first time I went to use it, it asked me. The way this worked is it actually dispatches to the runtime system a request for approval, and then that system service, after the system service displays a UI. The application doesn't display the UI. The application displays the UI, you can just click the button and go on through, right? So it actually calls into the system service, and the system service says, yeah, you're allowed to access this finance thing. And you can see that I have this little program called Intent Sniffer. It's available on our website, and it just shows you different things that are going on in the system. And here you can see the intent that was used to launch this demo to get that approval. And you can see it leak my account name in there. It's probably the appropriate thing for approval. All right. One of the other main, so that's the permissions system, and that's kind of the most obvious Android security feature, and the thing that if you are writing Android apps, there's a nice introduction to. on the developer guide, and it's the thing that I hope people understand, but that there's been a lot of confusion with. Binder is a new kernel mode IPC mechanism in Android, and it's maybe a little less well understood. Binder's kind of like a Unix domain socket, in that if you use Unix domain sockets, they're just for communicating locally, but they let you move file descriptors between processes. And so that means that if I've got two processes, one that can access a file and one that can't, the one that can access the file can just pass the open file descriptor to the one that can't. It lets you do privilege isolation, lets you do privilege separation, right? And it's kind of dangerous because you pass the file descriptor, you get in trouble, but generally it lets you have a more secure architecture where you can have something very privileged that does everything that's simple and part of privilege, and then something complicated and hairy that has lower rates. Binder is kind of like a, it's a remote RPC mechanism. It can move file descriptors, but it can also move binders. And that's like it's funny because the names conflict. It sounds really confusing, but a binder is just a reference to a binder interface. So you can move references to their own interfaces over this IPC mechanism. You can think of it like a file descriptor to a binder interface. So it also has marshalling code for primitive data types, so you can move strings and ints and stuff. And it also has a nice thing for wrapping up C or Java objects called parcelable objects. And it can move whole graphs of those. And it can, of course, move file descriptors and binders. So when you're enforcing permissions over a binder interface, so you write a service, say, or you write something that you want to have called by a lower rights part of the system, you're going to expose that some kind of method, right? So here's an example method that's exposed over a binder, and it is the shutdown method. So I guess it's going to shut down the device, not the kind of thing you want just anyone to do, right? So there's a permission on Android, and it's one of the permissions I like because it's simple enough that you can kind of understand. It's called shutdown, and what the shutdown permission does is it lets you shut down the thing. So this method has to enforce the shutdown permission, and it just calls check calling permission on the shutdown, and that automatically checks based on the context that binder interface is running in. It looks up who the caller is and verifies that they have that permission before it executes. So the system, we call this, but a normal application that you just install. And maybe a vulnerability would be if you could trick the system into calling this for you. All right, so now I'm going to make binders a little more tricky. So they seem like a really simple idea so far, right? They're just an RPC interface that can move references to themselves. Well, that reference to itself is something that the kernel validates that the sender has before it moves it into the receiver's address space, right? So I can't just pass in any binder, like say you have number 4 binder, and I don't have number 4 binder, and I pass in a 4 and just kind of hope that the kernel will give you a binder that you have a reference to and I don't. That doesn't work. The way that binders are marshaled through on Android is it verifies on both sides at the kernel level that the sender had it before they transmitted it to the receiver, which means that the recipient can actually be assured that the sender had it. So that means that a binder can't be forged and that a binder can be shared. So you can use this like an unforgeable token, right? You don't have to have a password or some random value that's hard to predict. You actually have something that the operating system can prove or can prove indicates access. And that this thing itself can then be an IPC mechanism. So this is used in the window manager for surfaces and layout parameter tokens and application tokens. And it allows you to do stuff like have APIs where you pass in the surface for something to be done, and it just performs the operation, and it doesn't worry about whether or not you have the rights for that, because the very fact that you possessed it was proof. So it makes permission checks really, really fast. All right. So as soon as we implement a mechanism like Binder, we need to get them somehow. And there's this thing called the service manager, and it's sort of the most basic way that we access all of it's like the directory service for binders, And it runs off of the context object. So there's this, it has a couple of methods, even though they're not, they're hidden, so you can't see them. But you can actually call them if you use reflection. List services and get service. So these methods let you look up binders for any system service on the device. And system services like the activity manager and the package manager and the account manager that I've been talking about are all exposed through this directory. And I should note that these system services are totally unrelated to that service site I was talking about before. These things are always running on the system. And so here's an example of what some of the system services on a typical device are. This is from my Nexus 1, I think. And you can see phone, right? And it's an iTelephony interface. And iPhone sub-info, and SIM phone book, and the ISMS, and disk stats, and application backup. These are all really cool features that you can access if you know how to call the kind of the RPCs that they expose. And they all enforce the Android permissions, the checks, the Android permission checks, on each of the methods of these. So when you call into them, if you build an app, you don't want to use the standard API, you can just call these directly up if you wanted to, and many people do. It'll probably break the next time the operating system updates because they didn't expose this stuff for a reason. But you know, there's also, especially when you're hacking on a device and trying to see what's there, it's a great place to look. One of the things that I thought was fun was there's an undocumented addition in the Froyo version of Android, the Dropbox service. And if you go and look in the source code, it's open source, you can just read the thing, and it's documented in the comments, but you know, it's actually hidden away, so you can't tell it's there. It's another way of making logs that are more persistent. And the thing about logs is that Android logs have been sort of a problem from a privacy perspective. One of the critiques that's going to be about Android is that people log things that they shouldn't log, and then just by having to read logs permission, applications can sometimes figure out your GPS location or other sensitive information about the user, because you can see it as a side effect of other things that happen on the device. Well, the Dropbox is a way of making logs persist between boots of the operating system. So, you know, that might cause some other kind of concerns. And so it's interesting to us forensically, and it's interesting to us from a privacy perspective. And well, these are definitely look at. System services. So these system services, right, that implement this these binder interfaces, they actually can be really simple. That's sort of the simplest one. I'm just going to skip over that and get to updates. So one of the things about Android updates is that they're signed, but they're signed in a way that doesn't actually identify the person who created the app. The updates are just, you know, I'm talking about updates for applications. Updates for applications just give you the idea of persistence of development, right? It says the same person who wrote the last version of this application wrote the next version of this application. It doesn't say, I swear that this is Jesse Burns and lives in San Francisco, right? It just says, it's the same person who wrote the last version. And so that's what allows you to update it. That's a really tricky thing because people used to think of signatures as proving identity. But if you've ever tried to figure out from looking at certificates exactly who they represent, even root certificates, it can be really hard. So, I'm sorry, I'm really short on time here. One of the things about system packages that's really fun is that they can have things like writing secure settings, so that's changing the settings that you can only usually change for the settings menu, installing packages, clearing the phone, and it's really easy to enumerate them on a device. So if you get a device and you CD into the data directory, you're going to find that you can't see anything in there. It's not executable or it's not readable. But if you pull data system packages.xml, where you CD into data system, you'll be able to pull a list of everything that's installed, where all of the permissions are for it, and you know, the keys that are used to sign those actors and that are used for the security decisions. And that gives you a map of where to pull all of those APK files. And also, you can just look in the system app directory, like I showed before, for just the system ones, although that'll miss things that were installed subsequently. And those can be really interesting. Um, so one great thing I like to do when I get a new device is I get a list of the system packages, I pull them off the device, and I use a tool, I used to use my Manifest Explorer tool, now I use this tool called APK tool to just extract all the Android manifest.xml files. And then I go through and I review the permissions. So one fun permission that you see, sometimes you see packages that are debuggable. And when you see like some funny things, like I found the StarDroid app and the Gallery 3D and the media uploader on the G2 that were all debuggable. And that means that there's this little binary called runAs, and you run it, it's set UID, and if you're running a shell, it lets you become any UID of a debuggable binary. Or if you hook it up to DBMS, you can actually access that process's address space. So, having debuggable binaries lets you, play in their address space. It's not a particularly great security idea. Another thing about them is that you can see when they have shared user IDs. So, for example, HTC on the Nexus 1 has some code that was installed as a system application. It doesn't look like it declares any rights, but when you look at its Android manifest, you see that it actually runs as a system. And so it has full rights. You can also see which of the files on your phone have access to your contacts. So, if you flip through, you might find that, say, that Facebook and Twitter application that you didn't want or necessarily need. For some reason, it has read contacts. I don't know why it has that, but it's surprising, and it's the kind of thing you should be able to review. And then one of the other things that's kind of fun here is if you look in settings, the settings application, you see that it has this activity it exports called the debug intent center, and it's also not documented. But if you type, so you might want to try that. I think I have a slide of it in a second. And then one of the other little things that I always find fun is I go find name and Android manifest XR draft A1 secret code. And secret code shows you the secret codes that are installed on the device. So this is a Nexus 1's list of secret codes. Sorry for the font, there's 8 of them there. These are like funny little codes you type in, and you get things like radio interface information and turning on logs and stuff. On the G2, you have 16 of them, and my wife has the G2, and she won't play with it very much. So I managed to pull the packages all off. Anyway, but I haven't actually managed to get all the secret codes typed in to see what they all are. But they sure sound fun. You can see what packages have released and have created them, right? Some of them sound kind of boring, but some of them are really interesting, like debug tool. That sounds fun. It's good secret code. The check-in provider. Check-in is the service that does over-the-air updates. So that's always fun. Fieldcast. That sounds like a good time. Some log and stuff. So when we're doing Indish and we're shelling into the device, if you're using an emulator, you're assuming that you're running a script, right? And if you're using any real device, it's going to be running as the shell. And the reason for that is, well, you could have conspiracy theories, but one of the main reasons for that is you don't want to have every device, when you pick it up and plug it into a computer, just automatically ask the key on it or pull all the keys on. So this shell account has a bunch of really interesting rights, including rights that you can't normally grant to applications when you install them. And so that makes it, without having the correct signature or installing them on that system partition. So you can do things with the shell that you can't normally do, like write settings, write secure settings, install packages, delete packages, backup. That's why you can do an ADB install, right? And an ADB uninstall. Those are really key rights. And it also lets us do things. Yeah, one thing it doesn't let us do. So here's an example of something it doesn't let us do. So there's the AM command that lets us call activity manager. So we say AM start native end, which means we're specifying a component, the shutdown activity. And because the shell account doesn't have the shutdown right, what we see in the log, or actually I think we see it printed around the screen, is, hey, we tried to start that intent, but it failed because it requires the permission that we want that shutdown. So, if, however, we use that same command line to start the debug intent center, which I mentioned we saw earlier. That sounds like fun. And up pops this little thing, and sure enough, here it is, a little thing that sends intents. And if you look, it's running a system, which means it has everybody. So that's good. And you specify the action, the data, the account. This isn't a security problem, because applications can't do this, right? Only people can do this. You have to actually sit down and do this to yourself. And anyway, it is a lot of fun. You can type Android intent action request shutdown and start that activity, and sure enough, it will shut down. So I have a list of kind of exploratory tools. Talk about these at other places, and be happy to go into them again sometime or in questions. But you know, it's really important to sort of be able to look at all the different spots on Android that people who customize the devices that we get have been hiding stuff. Sometimes we find cute new things like the Dropbox, and we might want to look into those log files and see what they've been logging on our devices. After all, they're part of the forensic trail. You can see all kinds of stuff in Linux, like the proctors, sysods, and the packages.xml. Is this great definition? But just wanted to talk a little more about permissions. So one of the kind of key points I wanted to discuss here today was that permissions are really important to make understandable. And whatever you do to extend the Android platform to make it more secure, you need to make sure that a user can understand it so they can make a real choice. And that means when you're developing apps, they have to actually enforce the permissions that you have, and that when you design a permission, you have to think about who the recipient is, right? It can't be something like a native code execution permission. That's not something that normal people understand. It's something that only developers understand. One of the cool things that we're seeing in almost all of the mobile platforms, including Android, is that the user is no longer the principal, right? You log into a computer, and the apps that are running on it don't just run as Jesse or just run as you. They run as whatever program they are, instead of as instead of having every possible right. And that lets us have sort of the least privileged environment, and makes it so that we have to do creative things security-wise to protect all of the information that we have. But you know, imagine if the CNN website read your Gmail, right? Nobody would read CNN because they'd be terrified. So we kind of have this idea already on the web with the same origin policy, and now that's spreading into modern mobile operating systems. I think that's a really cool thing that I'd like to see run into other platforms. Unfortunately, it requires a secure UI, and making a secure UI is really hard. People don't have an intuitive grasp of which application necessarily is running at a time, and that can be something that you have to really look at too. You don't want to start having the kinds of phishing attacks we have on web browsers happening in applications. Also, one of the things that I think is really interesting to learn from mobile applications is that having an authority like Apple can substitute for having a technical permission, a technical protection, like a permission system, right? One way of protecting users is just to have someone who looks at every app and says, hey, yeah, this is good. It doesn't let people tether. That would be an insecure thing. It doesn't read your email and send it all off to Wikipedia. This is a great app. I don't personally think that's a great thing for me, but it does definitely seem to be successful. Another thing that I think is a cool lesson from sort of mobile security is that a lot of restrictions are ineffective and are actually counterproductive. So people have tried to stop people from getting root on their phones. And so what we've got is a lot of people writing good exploits that are reliable, that they can put on websites, that automatically own phones that don't allow this, right? Because people like, if I want root on my own phone, I'm going to spend a lot of time on it. If you want it, you're going to spend a lot of time on it. People are going to polish that stuff up and put it out so that everyone can share. If you're writing malware, those exploits are now available for people with bad intentions too. So it undermines the security of the whole system if you encourage people to publish root exploits by keeping legitimate people who might want root away from it. Also, one of the first things that all these root exploits do, like if you read the guides, They all go like, oh, do this, do this, do this, congratulations, you have root. Very important next step is disable updates, right? What that does is it makes the phone network into a giant welcome sign for botnets, right? The only worm that's been out there for an iPhone was attacking jailbroken phones, right? The people that write this stuff, they often do really crazy stuff, like they throw setuid su binaries onto the file system that anyone can exec, right? That means I can download an app, it has no permissions, it execs su, and bang, it's root, right? Goodbye, whole security model, right? So this is not the kind of thing that you want people doing. Also, 15-year-olds are really smart, so some of those restrictions around tethering, there was this kid who made a 15-year-old kid who made a flashlight app for the iPhone going onto that iPhone store. The person was actually soft crossing for tethering. Anyway, some of the effective restrictions. So, by not exposing interfaces for doing legitimate kernel extension to third-party developers, Android has blocked legitimate AV from being able to do that kind of thing. And that means there's no hook-based AV systems on Android. There are programs out there that do stuff like MyLookup and look at binaries, and there's lots of ways that you can inspect the code in the machine to make sure it's safe. But you can't actually see if someone's put a rootkit in, and you can't do like all the hooks on reads to get malware before it runs. Fortunately, little or no malware is exploiting this. And certainly if you are an enterprise or some big customer or the open source community who wants to collectively get together, you can build a new distribution of Android that would have effective, powerful restrictions like this, or some way to install kernel modules or UAV or something like that. It's just not really much yet. But some of this has been tried on other platforms. We'll have to see how successful it is. Unfortunately, permissions are often too complex for users to understand. They don't want to read. But I think other solutions are often even worse. You can definitely imagine extending package manager to allow for maybe an open source group or a vendor to affirm that applications are good before they're allowed to install. That'd be a great possible addition to Android's security system. But security extensions that are designed to restrict native code are not likely to work because the whole Android system wasn't built with that in mind. And so you're just taking some idea from maybe Java or from the BlackBerry or something and trying to apply it to a place that doesn't really fit. I've also experimented a bit with repackaging applications, but it's largely ineffective because security exceptions are a really common side effect when an API fails for security reasons. So there is a great paper that's been published called Apex, and they are talking about a framework they built to dynamically grant rights to applications. The problem with that is that now users are going to have to make security, be prompted about security decisions later. But there could definitely be something very valuable there, especially from very sophisticated users. And I think that kind of thing, if it's not too ugly, could be useful. But also, I get concerned when I see things like that approach, though, because it encourages the idea, this very bad old security idea, that security is a trade-off between with convenience. And I really think that's wrong. There's no such thing as security without convenience, right? Because that trade-off gets lost every single time. So it's not there's not a trade-off. There's a good security system has to be designed for convenience. Anyway, I think I'm out of time here, so I'll take a question or two if I have a moment for that.
I guess that's time for maybe one or two questions. No?
All right, I'll talk about one last security mechanism that's new in Android, and it illustrates my point about updates. So, Cupcake, right? That was version 1.5 of Android. Donut, 1.6 of Android. Fair, 2.1 of Android. Froyo, 2 of Android. Lovely new versions. Each one of them has a branch where people are adding security fixes, right? But there's a new security feature that appeared in Donut called protected broadcasts, and you won't find a lot of documentation of it because while the source code is open, an explanation hasn't appeared. There's a couple of comments, and it's pretty obvious what it's doing. It's stopping people from sending broadcasts that are for things that you kind of know the system should only be doing, right? So it's stopping third-party apps from doing things like saying, hey, the system just docked. That's probably because you only build a security mechanism if you're trying to stop something. So obviously somewhere in there was something that wasn't properly checked. And so this has been added as a second layer. So we had 25 of them in the version Donut, 45 of them in Eau Claire, and we have 50 of them in Frozen. So if you're deciding to ship a new device and you're using an old version of Android, there's obviously already a security protection that's been augmented in a new version that isn't available in the old version. Right? That's just something you should keep in mind, right? I mean, what it means to run the latest version of this platform is to run the very latest version, right? Not to run one version back and try and patch and patch and patch. You just want to stay on the top of it. That's what it's going to keep you.
If there are really no more questions, then thanks for suggesting.